One of the big projects you worked on at Dropbox was migrating away from
Yes,
S3.
yes, yes.
So, why did Dropbox migrate away from S3?
Yeah, that was a desire at the company for a long time. From even before I was there. So I started Dropbox in 2012. And I spoke to Drew, the Dropbox founder, I think in 2010 about this project. And so I think there was a desire to control the destiny of the company from a strategic perspective. I mean, at the time, this is before Dropbox kind of reshaped itself as being more about collaboration. But at the time, it was a file sync and share category. That was the market sector. And owning the file system was really valuable to the company. Ultimately, we saved a huge amount of money. I mean, and this is before the public company went public. We really drove massive cost efficiencies through the project. But it was hard, in a way that I think it'd be very difficult to emulate without a huge investment. And I do think that there is a benefit to an organization from having hard problems to solve. Because if you have a company with extremely hard technical challenges, you can attract engineers who like working on those hard technical problems. And when they've solved those problems, they cycle off and work on different parts of the system. So, after we all worked, we had such a great team. It was a very, very small engineering team. And after we kind of shipped the storage system reliably, we all went off and Jamie went and redesigned the sync protocol, the desktop client, and I worked on the file system and the distributed databases. And so yeah, there's value to a business to have that level of technical investment, but it is it's like having a baby, and then you've got to raise the baby. You can't just build a system like this and that's it, we're done. You own it, and you have to keep investing in it.
Did did S3 do any counter negotiation before you set out to leave them? They say like, oh, we'll cut you a deal if you stay.
I guess I'm allowed to talk about this now. It was a long time ago. Yeah, for the longest time there, I don't think they were particularly aware that this was happening. But the data center folks talk, and certainly it was noticed that Dropbox was buying up a lot of data center space. So yeah, we had obviously at the scales that we were at. I mean, we were negotiating very good rates with Amazon. We weren't paying sticker price; we're paying very, very, very good discounted rates. But yeah, at a certain point, they weren't able to meet our cost efficiency because when we launched the system, it really was more efficient than S3. And that's for a variety of reasons. One was that we were using kind of new experimental disks called shingled magnetic recording. We were the first ones, I think, to use these disks at scale. And two, we had a very tight understanding of our workloads. So we were able to design the system specifically optimized for our workloads, whereas S3 has to design the system for everybody. So, it got to the point where, Amazon would not have been able to offer us a more competitive deal because we had a more efficient system. I wouldn't recommend another company do this right now. But I think at the time, it certainly made sense for us as a company.
Can you give an example of a tight understanding of your workload leading to like something you could do that S3 couldn't?
Yeah, absolutely. So, for example, I know that, I'll try not to leak any confidential data, right? But when you upload a file to Dropbox, there is a pattern of access, right? So typically people access the file very quickly, shortly afterwards, because you're sharing it with someone, or maybe Dropbox is processing that file to generate an image preview, and then it decays at a certain rate. And so we understand in general the average block size, and we understand also the access pattern. So we could do things like at a certain point, we had these two clusters. One was designed for kind of temporary storage that was kind of storage inefficient, but access efficient. So it was very cheap to read and write to, but it was inefficient to store. And data would get written to there first, and then in the background, it would get moved in bulk to this colder storage system. And this colder storage system was far more static. And so it was able to have kind of more efficient algorithms and be written to in bulk. And if it went down for writes, that was no problems because it wasn't in the live path. And so we're able to trade off, again, like systems is all about trade-offs. So we're able to trade off the live data write path from the long-term read path. That was one of many examples where knowing the size of your data, where it's accessed from, how frequently it gets accessed, how long it takes to delete that data, you can really tune a system to your workload. Stuff like looking at even things down to knowing how much power to put in a rack. You have a rack of hardware. There's a power distribution unit, a PDU, at the top of that rack. It has a circuit breaker which can handle a certain number of amps. We would have to figure out, how many amps are required for that rack based on access patterns. And there were times where we got it slightly wrong. There was times where we got maybe a bad batch of hardware and disks were failing too frequently. And as a result, we were re-replicating the data more regularly. And I was getting, messages from the data center team saying, hey, we're running the racks really hot right now. So that's the level of optimizations you can make when you get to that scale. But again, that's multi-exabyte scale, million hard drive scale.
Yeah, when I was reading about this migration, I saw somewhere in the migration, you initially started with Go, and then the racks or something that you're running on the hardware itself was ooming too much or requesting too much memory, and then you migrated to Rust.
So initially, the prototype was in Python, if you can believe that. And to be fair, Python is actually pretty efficient for I/O. I think people give Python a bad rap for I/O-bound workloads. It's pretty good at I/O, but obviously not great for concurrency, not great for memory management, and very hard to refactor. And it was critical the system was correct. And so we migrated everything to Go, and we built most of the storage system in Go. This is before Go was in general availability. I think this is before Go was GA. And we built the system in Go. Go's a great language for concurrency, a great language for proxies. It's a really well designed for like servers that moved out of one place to another place. At a certain point, though, we would have, let's just pick a number. Let's say 1 million. Let's say we have 1 million nodes in the system. And every node has some amount of memory, some amount of disk, some amount of sheet metal in the chassis, right? And we would itemize all these things. You'd have a pie chart of how much money is spent on all the things. And it would have stuff like, sheet metal and screws and stuff. And so you're trying to optimize the storage. And a big problem for us was the amount of memory these nodes were using. Not just the memory they were using, but the unpredictability of it. With Go having a runtime and in a storage system, an out-of-memory error is pretty bad. Because if a node runs out of memory and restarts, that looks like a disk failure. So that looks a lot like a disk has failed and has to be re-replicated. And so a batch of nodes ooming can lead to cascading failures throughout the system. Because maybe, I remember a time, it was a band, it might have been De La Soul, I can't remember. There was a band released an album on Dropbox. So there was a big spike in load to a few files. So it was very, very high bandwidth, and it caused the machines to oom. So those machines oomed, those disks oomed. And so as a result, no problems. The system went to try to recover that data from a whole bunch of other replicas, right? Now, all of a sudden, you've taken one fire hose worth of load coming in, and you've turned this into 7 fire hoses worth of load coming, because now you have to do a more expensive reconstruction operation, right? So now you've 7x the load. And these are the kind of cyclical kind of behaviors that can lead to something called congestion collapse. Congestion collapse is when workload to a system crosses a threshold where it all kind of collapses. So designing against congestion collapse is really the hardest part, or one of the hardest parts of Magic Pocket, which is the name of the storage system. So ultimately, we switched to Rust for the storage nodes themselves. And this is before Rust was in GA, so that was a bit of a risky move. But we rewrote the switch to Rust coincided with getting rid of the file system entirely on the disks and directly addressing the disk heads. So there's an instruction set. I think it's called ZBC, zone-based block control, something like that. There's an instruction set for accessing disks that we were using. The disk manufacturers gave us the draft specs of these new disks, and we were operating off the draft specs and directly controlling the disks. And so all that product was tied up together into a product called Discotech. It was the disk technology project. And ultimately, if you look at that pie chart, one, congestion collapse stopped and reliability improved. But if you looked at the pie chart of where all the money was going, it really shifted to be almost all disks. And what we wanted to do is get that pie chart to be almost all the money spent on disks and as little money spent on RAM, on compute, on network, on power, on sheet metal, etc.
The cascading failure you mentioned, was there, so that happened and then there was a post-mortem.
I don't think we needed a post-mortem. I think we knew as it was happening. I think when I was getting paged in the middle of the night on these things, you'd be pretty evident. And so, look, this is this is an argument in favor of the cloud. And imagine you've spent hundreds of millions of dollars on a storage system, and it's out in production, and it's on physical hardware. You can't just go and put new memory chips in every one of them. I mean, you can, but you have to pay people to come in and swap them out, And so that's a tricky place. And so and this is what I love about industry, because in like some of the more challenging moments on Magic Pocket were stuff like in 1 week, just a weird coincidence, 2 trucks crashed that were delivering service. So there's 2 trucks showing up to deliver racks. So they both crashed. I don't know, the drivers were okay. So we lost capacity for 2 weeks. So we lost capacity for more than 2 weeks, for probably 6 weeks. What do you do? What happens, it's the equivalent of your disk filling up on your laptop, except it's a million disks, and you can't tell the customers to go away. You can't delete their files. So a lot of tricky capacity work, and ultimately what that led to was trying to build in all these protections against the unknowns. Making sure we had the right amount of buffer planned out for anything bad that could happen. Making sure we designed the system so there couldn't be congestion collapse, so there wouldn't be memory spikes. And at one point there's a process called, I think it's called FMEA, which is like a threat modeling process where you had a big spreadsheet and you kind of write down every bad thing that could possibly happen, and then how bad it would be if it happened. Existential risk. Does someone die? If there's a fire in the data center, all these kind of things get put into this spreadsheet, and you kind of do a bit of a almost pre-mortem kind of work to figure out all the potential failure modes, and then design around them. And I love that work. I really I don't know. I do like the firefight. I can't say I like getting paged because I've spent my whole life on call, but I do like that rubber hits the road stuff. I like that. Wow, there's congestion collapse and there's no one that can help you. And so you've got to think through this problem.
When I worked on infrastructure at Instagram, we had this concept of DEFCON knobs, which are basically these configs that you could flip that would gracefully degrade your system, where you can still operate it, but maybe in the case of Dropbox, you store less replicas. So you take on a temporary increase of risk in losing data because you need to. Did you have something like that, and did you flip it in that type of case?
Never when it came to durability. So, I mean, we just had a just absolute zero, non-negotiable, like there was no room for negotiation on users' durability. And so we had those knobs for background processes for CPU and memory, for example. So if there was like a spike in load, you could turn off background processes and turn off the test load, for example, on the system. Eventually, we built this system called Trampoline. And what Trampoline did was, which actually was, it saved us a ton of money, right? If we ever got too close to the threshold, we would just start writing data to S3 because it's right there, right? So it's you can run your capacity way closer to the edge if you're willing, under worst case scenarios, just to dump 30 petabytes on S3 and then move it back when it's done. And now that didn't happen very often. We would do it to test it. We would do that just to make sure the system worked. But being able to have a escape hatch for worst case scenario was really nice.
I see. So S3 is kind of it's like elastic storage.
Exactly.